The sequence form. In the reduced strategic form, pure strategies are only partially specified by omitting moves at information sets that cannot be reached because of an earlier move. In the sequence form, pure strategies are replaced by an even more partial description of sequences which specify a player's move only along a path in the game tree. The number of these paths and therefore of these sequences is bounded by the number of nodes of the tree. However, randomizing between such sequences can no longer be described by a single probability distribution, but requires a system of linear equations. A sequence of moves of player I is the sequence of his moves, disregarding the moves of other players on the unique path from the root to some node T of the tree, and is denoted the row I of T. For example, for the leftmost leaf T in figure 3.3, this sequence is LS for player 1 and L for player 2. The empty sequence is denoted the empty set. Player I has perfect recall if and only if rho I of S equals to rho I of T for any nodes S, T in H, and H in HI, then the unique sequences rho I of T leading to any node T in H will be denoted the rho H. Perfect recall means that the player cannot get additional information about his position in an information set by remembering his earlier moves. We assume all players have a perfect recall. Let beta I be a behavior strategy of player I. The move probabilities beta I of C fulfill the summations of beta I of C equals to 1, summing for all those C in CH. Beta I of C is greater than or equals to 0 for H in HI and C in CH. The realization property of a sequence rho of player I under beta I is beta I of rho equals to the multiplication of a beta I of C multiplying for those C in rho. An information set H in HI is called relevant under beta I if beta I of rho H is greater than 0, otherwise irrelevant. In agreement with the irrelevant information sets as considered in the reduced strategic form, let Si be the set of sequences of moves for player I. Then any row in Si is either the empty set or uniquely given by its last move C at the information set H in HI. That is rho equals to rho H C. Hence, Si equals to the set of the empty set union the set of rho H times C, such that H in HI and C in CH. This implies that the number of sequences of player I apart from the empty sequence is equal to his total number of moves, that is, the size of Si equals to 1 plus the summations of the size of CH, summing for all those H in HI. This number is linear in the size of the game tree. Let beta 1 and beta 2 denote behavior strategies of the two players, and let beta 0 be the known behavior of the chance player. Let A of T and B of T denote the payoffs to player 1 and player 2 respectively at a leaf T of the tree. The probability of reaching T is the product of move probabilities on the path to T. The expected payoff to player 1 is therefore the summations of A of T times beta 0 of rho 0 of T times beta 1 of rho 1 of T times beta 2 of rho 2 of T, summing for all those leaves T. And the expected payoff to player 2 is the same expression with v of t instead of a of t. However, the expected payoff is nonlinear in terms of behavior strategy probabilities. Beta I of c, since the terms beta I of rho I of t are product by 3.21. Therefore, we consider directly the realization probabilities beta I of rho as functions of sequences rho in Si. They can also be defined for mixed strategies mu I of player I, which choose each pure strategy pi I of player I with probability mu I of pi I. Under pi I, the realization probability of rho in Si is pi I of rho, which is equal to 1 if pi I prescribes all the moves in rho and 0 otherwise. Under mu I, the realization probability of rho is mu I of rho equals to the summations of mu I of pi I times pi I of rho, summing for all those pi I. For player 1, this defines a map X from S1 to R by X of rho equals to mu1 of rho for rho in S1. We call X the realization plane of mu1 or a realization plane for player 2. A realization plane for player 2 similarly defined on S2 by a mixed strategy mu2 is denoted Y. Realization planes have two important properties. Correct, we call X the realization plane of mu1 or a realization plane for player 1. Okay. Proposition 3.10. A realization plane X of a mixed strategy of player 1 fulfills X of rho is greater than or equals to 0 for all rho in S1 and X of the empty set equals to 1, summing for all those X of rho H of C, summing for all those C in CH equals to X of rho H for all H in H1. Conversely, any X which maps from S1 to R with these properties is the realization plane of a behavior strategy of player 1, which is unique except at irrelevant information sets. A realization plane Y of player 2 is characterized analogously. For the second property, two mixed strategies are called realization equivalent if they reach each node of the tree with the same probabilities given any strategy of the other player. We can assume that all chance probabilities beta 0 of C are positive by pruning any tree branches that are unreached by chance. Proposition 3.11. Two mixed strategies mu I and mu I prime of player I are realization equivalent if and only if they have the same realization plane. That is, mu I of rho equals to mu I prime of rho for all rho in Si. These two propositions to be proved in exercise 3.13 imply the well-known result by Kwon, 1953, that behavior strategies are strategically as expressive as mixed strategies. Corollary 3.12, Kwon's theorem. For a player with perfect recall, any mixed strategy is realization equivalent to a behavior strategy. Proposition 3.10 characterizes realization planes by non-negativity, and the equations 3.11. A realization plane describes a behavior strategy uniquely except for the moves at irrelevant information sets. In particular, the realization plane of a pure strategy, that is, a realization plan with values 0 or 1, is as specific as a reduced pure strategy. A realization plan represents all the relevant strategic information of a mixed strategy by proposition 3.11. This compact information is obtained with the linear map in 3.23. This map assigns to any mixed strategy mu I, regarded as a tuple of mixed strategy probabilities mu I of pi I, its realization plane. Regarded as the tuple of realization probabilities mu I of rho for rho in Si. The simplest of mixed strategies is thereby mapped to the polytope of realization planes defined by the linear constraints in proposition 3.10. The vertices of this polytope are the realization planes of pure strategies. The number of these vertices may be exponential. However, the number of defining inequalities and the dimension of the polytope is linear in the tree size. For player I, this dimension is the number size of Si of variables minus the number 1 plus the size of Hi of equations 3.24, which are linearly independent. So it is the summations of the size of Ch minus 1, summing for all those H in Hi. We consider realization planes as vectors in X in R to the size of S1 and Y in R to the size of S2. That is, X equals to X rho such that rho in S1 where X of rho equals to X rho equals to X of rho. And similarly, Y equals to Y tau such that tau in S2. The linear constraints in proposition 3.10 are denoted by E times X, capital E times X equals to small e. X is greater than or equals to the 0 vector, and capital F times Y equals to small f. Y is greater than or equals to the 0 vector. Using the constrained matrices capital E and capital F and the vectors E and F, the matrix E and the right-hand side E have 1 plus size of H1 rows, and capital E has size of S1 columns. The first row denotes the equation X of the empty set equals to 1 in 3.24. The other rows for H in H1 are the equations X of row H plus the summations of X of row H times C, summing for all those C in CH equals to 0. In figure 3.3, the sets of sequences are S1 equals to the set of the empty set L or LS LT, and S2 equals to the set of the empty set L R, and in 3.25, the capital E equals to the following matrix. The first row and the first column is the entry of the first row, and the first column is 1. The entry of the second row is -1, 1, 1, and so on. The second entry of the third row is -1. The fourth entry and the fifth entry of the third row are 1s. Little e is the vector 1, 0, 0. Capital F is represented as the following matrix. The first row of the first element of the first row is 1. The element of the second row is -1, 1, 1. Little f equals to the following vector 1, 0. Each sequence appears exactly once on the left-hand side of the equations 3.24, accounting for the entry 1 in each column of capital E and capital F, the number of information sets, and therefore the number of rows of capital E and F is at most linear in the size of the game tree. Define the sequence form payoff matrices A and B, each of dimension size of S1 times size of S2 as follows. For row in S1 and tau in S2, let the matrix entry A row tau of A be denoted by A row tau equals to the summations of A of t times beta 0 of row 0 of t, summing for all those leaves t such that row 1 of t equals to row 2 of t equals to tau. The matrix entry of B is this term with B instead of A. An example is shown on the bottom right in figure 3.3. These two matrices are sparse since the matrix entry for a pair row tau of sequences is 0, the empty sum, whenever these sequences do not lead to a leaf. If they do, the matrix entry is the payoff at the leaf or leaves weighted with chance probabilities of reaching the leaves, if there are chance moves. Then, by 3.22, the expected payoffs to players 1 and 2 are x transpose times A times y and x transpose times B times y respectively, which is just another way of writing the weighted sum over all leaves. The constraint and the payoff matrices define the sequence form of the game.